I am Jeff Riemann from Formalloy. We are based in San Diego, California, specifically Spring Valley. We are exhibiting here at the show. We're in booth 539. We have a lot of part examples in our booth, so after the panel, if you'd like to come down and take a look, feel free to stop by. I'll give a little brief introduction about what we call laser metal deposition. Others call it directed energy deposition. There are numerous terms to describe the same thing. I'll assume that most people in here have at least some idea of what this is, but I'll go through sort of a brief description of what the technology consists of. So essentially you have a focused laser beam that aligns with a powder focus, which aligns with a substrate, and when all those converge in a common point, you're able to deposit metallic materials to a substrate. So it creates a melt pool, and you can either move the deposition head or you can move the substrate and lay down material. That's essentially laser powder welding, if you will. Now the one key thing that I really love about this technology is it's extremely flexible. So we are not limited by having to build parts off of a build plate. We can build parts on all sorts of things, whether they're castings, forgings, just other machine parts that have been machined and maybe need a feature added. We can apply coatings to those things, or as some people call cladding. And we can work with multi-materials. We do bimetallics all the time. So if you have say a mild steel substrate and you would like to add a stainless material or a nickel-based alloy or a cobalt-based alloy on top, that's relatively easy for us to do. And we also don't have a powder bed to contend with. So if you want to take a part from our system and move it somewhere else, it's fairly easy to do that. So if we're going to talk about how we integrate direct energy deposition or laser metal deposition into a production application, I guess first we have to talk about what can we do with this. So I just touched on this a little bit in the previous slide, but what are we going to look for? So obviously additive manufacturing applications where you're building a part from scratch. That's fairly obvious. Things that might be less obvious are repair or remanufacturing type processes. If you have shavs that wear down over a given period of time, we can repair and remanufacture those. If you need specific areas on parts to have a specific alloy added to them, let's say a carbide material, we can do that. And we also have a fairly unique capability of creating gradient materials and bimetallics. So if you come to our booth, we have an example of a part that starts at its base as a stainless alloy, and we gradually transition it layer by layer by layer to a nickel-based alloy. And we can do that relatively easily because we have multiple powder feeder sources on our machine, and just using different G-codes, we can define how much powder from each feeder goes into the head and automate that process, so there's no, you don't have to pull out hoses and plug them in. It's pretty hands-off. So those are all applications that we consider excellent candidates for directed energy deposition, and if there's enough volume, then we look to how do we do this in a production manner. So the material considerations. We can work with a lot of materials. Probably the biggest takeaway from this slide, which I don't call out but I possibly should, is that titanium alloys and aluminum alloys are fairly, they add a complication in that they're dangerous to work with in air. So you have to consider that when trying to integrate into a production application. You could envision that, if you have a machine that's depositing nickel, it's not a big deal to expose that to air and move it from point A to point B and then process it somewhere else. Titanium, that may not be the case, or aluminum, that may not be the case. You might need to take into consideration some of the safety aspects. But that being said, laser metal deposition is capable of depositing all of these different types of alloys, all of which we have worked with in some extent, specifically nickels, cobalts, irons, carbides, coppers. We have the most experience in those areas. Formalloy specifically does, and the gradients and bimetallics as well. And one unique thing that you may not know, we have deposited magnetic materials, so we can take alnico powder and we can deposit it and magnetize it and basically 3D print magnets with it too. So again, it's very flexible. So again, focusing on production. So how do you identify manufacturing opportunities for directed energy or laser metal deposition? Manufacturability. So I think we all know that if a part can't be produced in traditional methods via machining, that's where additive manufacturing is great, right? So that's an obvious one. Lead times. If you've got castings, forgings, things that require a lot of tooling. I think one of the panels I listened to yesterday, there was a really good term thrown out called the tyranny of moulding, which most of you could probably identify with. If you have long lead times and costs associated with making molds, that's something that we can maybe not completely avoid, but maybe we can help with. Material costs. So if you start with a billet of Inconel and you need to remove 80% of that, it's likely more cost effective to build it with additive manufacturing. And then last, and one that I think is sometimes overlooked from an additive manufacturing perspective, is repair. This is especially true Department of Defense. If you've got old fighter jets that have been operating for 30, 40 years, and the suppliers for these components may not be in business anymore. Maybe they've been acquired 3 or 4 times, and the guys who used to make these parts are no longer working. You have to find a different supplier, and maybe that's not acceptable to do. So can you repair those parts acceptably and utilize the parts that you have? We see a lot of interest from our customers in those types of applications. So when you're looking at integrating with production, especially if you're considering robotics, we are more of a traditional CNC machine. We run our machines with G-code, and sometimes that provides a lot of advantages, but sometimes it's not the best solution. Sometimes robots are better, and there are certainly programmability considerations to take with that. Teach tracing, obviously, is something that robots are better at doing than CNCs. CNCs are better at other things, so I would highly recommend taking those things into consideration. Luckily, there are some software solutions that over the last, let's say, few years have made that a little easier to overcome, especially with robotics. Taking 3D models and generating tool paths in robotics is not undoable now. It's fairly straightforward, but still there are differences, especially in quality. CNC machines tend to have better motion quality. There's less axes moving. You can tend to get better quality off of a CNC or Cartesian type system than you can off of a robot. So maybe that's important, maybe it isn't. Throughput. So the main thing I think about for production and additive manufacturing is, I guess I'm assuming that there's always a post-processing step. I don't think there are many technologies out there where you can, especially from a metals perspective, that you can take off the machine and plug onto an assembly. We're not quite there yet. So most additive metal processes are going to require an EDM step. You got to cut parts off build plates. You've got to finish machine the critical fit-up areas that need high tolerances. How are you going to do that? If you've got 1,000 parts, it's probably not cost effective to manually take it out of one machine and fixture it in another machine and indicate off of something, and it's going to be too slow. So implementation of standard work holding devices into additive manufacturing systems like our system is something that we have a lot of interest in development work going into. We don't have an off-the-shelf solution for that right now, but that's something that we're getting towards. One of the challenges with that is the heat that we put into parts. So a lot of work holding devices for machining centers don't come into those or work in those high heat type of applications. So there's things to work through there. There's quality components. So how are you going to inspect your parts? Are you going to use touch probes like Riemann probes? Are you going to use laser scanners? How are you going to verify that you're getting a finished part that meets dimensional requirements? And there's also the in situ process monitoring aspects and determining if you have defects in your part. And then last but not least, something I always like to consider with integration and production is what do you have laying around? We have a lot of customers that have a lot of robots, and maybe they have a cell that doesn't get used very much. And if you're asking someone to spend $1 million to integrate a full production line, that might be too expensive to rationalize the cost. So maybe we can cut that down substantially by utilizing existing equipment, whether it's CNCs that you have or robots that you already have. So common components. So these are the main components that are required to work with laser metal deposition. Now, Formalloy has a solution, what we call our LMD engine, essentially. It consists of a deposition head, a powder feeder, a gas manifold, and a laser. With those components, you can perform directed energy deposition if you supply the proper motion system, optics, or the chiller, laser safe enclosure, dust collectors, and of course metal powder, which I'll touch on lastly on this slide. But essentially our turnkey system, or our LMD engine, it enables those with robots or CNCs that may want to integrate this process for production applications. It allows us to do that with relative ease. So when we started working with metal deposition, we were, I'd say, not frustrated, but it's challenging to find good suppliers for all of these components. You can buy, other people sell deposition heads. We're not the only ones. You don't find a lot of people that also sell powder feeders, and you don't find people that also have the process know-how to work with all of the materials that we work with. So we try to be sort of a full suite provider for laser metal deposition, where if you need a full turnkey system, we can provide that. Maybe the turnkey system doesn't really fit your needs. Maybe the robot application or the robot cell integration meets your needs. Well, we can provide the components to do that, but I think critically we also provide the process know-how, because it's one thing to just get a box of parts and here you go, have fun integrating this stuff. But even if you can integrate it, then you have to learn how to run it. You have to know what to look for. And that's something that we have a lot of experience with. I will say also we are laser agnostic, so you don't require a single type of laser. We don't work with only an IPG, for example, or a laser line. We work with all types of lasers, so if you have specific laser needs, we also have solutions for that. So as I said, metal powder. So this was kind of touched on earlier in Dr. Gao's presentation, that not all powders are created equal, and there are certain things you can do with metal powders to prep them to be better ready for the additive process. And that's another thing that is absolutely critical for this process. Sourcing powders, where they come from, validating that they actually work properly in the process. As an example, we have found certain grades of Inconel, their Inconel 625 have, although they're technically they're Inconel 625, they have too much silica content in them, so they will create, as some people call, fish eyes, which creates porosity in builds. So knowing what to look for and knowing how to avoid those pitfalls can save you a lot of time. I think that was something that was touched on with the Haynes. My Haynes cracks, this guy's Haynes doesn't crack. Why? Well, it probably came from two different places, and it might meet the alloy requirements, but there may be something teeny tiny difference about that that's causing the variation that you see. And again, Formalloy, we help you with that because we've experienced those things firsthand. So the optional components for integration into production. So again, robots versus Cartesian. That for me is a big question because it's really going to dictate how you program your system and how it's going to integrate with the other equipment around you. Work holding, as I also touched on, there's varieties of different solutions for work holding, but some of them are not as well suited for this process as others are. Then subtractive processing. If you may not require any subtractive processing, especially if it's, say, an overlay type application with adding carbide. You may not need to subtract parts, but in other situations you may. And you may need to bead blast, you may need to extrusion hone, you may need to do all sorts of different things to get to your finished part. So really the takeaway from here, I mean, I know there's a lot of questions that remain from this, but I guess I'm hopeful that I've demonstrated that we have solutions for production integration, and that there's certain things I can't talk about due to NDAs that we have with certain customers of ours, but we're doing this now, and we have solutions that are ready to be integrated now. And if you'd like to learn more about what our capabilities are, I guess you could ask me how we can help you with that.